So, formal charge gives us a way to evaluate non-equivalent Lewis structures. And before we talk about evaluating these non-equivalent Lewis structures, let's first talk about how to calculate formal charge. So, formal charge gives us a way to make sure that we are attributing the electrons that are shared to individual atoms. Now, we know that these electrons are not attributed to individual atoms because they are in covalent bonds, but this is really just a bookkeeping method. So the two things that we're going to need to keep in mind is how many electrons does the atom have, or how many it has in the molecule, versus how many it brought with it. So how many does it have in the current molecule versus the valence electrons it would have if it was on its own. So with the way that we find the valence electrons that it has in the molecule is that we split up the bonded electrons. Now that just looks like multiples, sorry about that. We split up the bonded electrons and the atoms get to keep control, if you will, of their own lone pairs. So, for example, these are the electrons that oxygen would be given or would say that oxygen has in this molecule. So, 2, 4, 6 in the molecule. Carbon has half of each set of bonds, so 1, 2, 3, 4. Oxygen has half of these bonded electrons plus its lone pairs, so it has 6. Now, oxygen has 6 valence electrons normally, and carbon has 4. Having an equal number of valence electrons and then an equal number in the molecule means a formal charge of 0. We treat this or calculate it the same way that we treat ion charges. Now, the rules are that the formal charges have to add to the charge on the species. This has an overall charge of 0. These have to add to 0. And they should be as close to 0 as possible. Any negative formal charges should be on more electronegative atoms. So if we want to evaluate a molecule based on formal charge, we're going to use these rules, had versus what has in the molecule versus what they brought, and we're going to look at those rules. So a question might say, evaluate these using formal charge and propose which one is the more likely structure. If we have a structure that follows these rules, that would be a more likely structure. So first thing I like to do is, I'm coming into so much trouble here. This is how I always do this. First thing I'm going to do is split my bonded electrons. And when I split my bonded electrons, I'm just sort of erasing down the center. Makes it an easy visual to see how they're split there. Nitrogen has 1, 2, 3, 4, 5, 6 in the molecule. Carbon has 4, half the bonded atoms, and sulfur has 1, 2, 3, 4, 5, 6. In this molecule, this carbon has 1, 2, 3, 4, 5, 6. Sulfur has 4, and nitrogen has 1, 2, 3, 4, 5, 6. Now, nitrogen brought 5 valence electrons, carbon brought 4, and sulfur brought 6. So I can already see that looking at the structure on the left-hand side, we'll call it structure A and structure B here. Looking at structure A, 4 and 4 are equal, 6 and 6 are equal. So those are formal charges of 0. If it brought 5 and it now has 6, it's like it has an extra electron. So nitrogen's formal charge is -1. Here, however, carbon has 6, it brought 4, that's a -2. Sulfur has a +2, and nitrogen here has a -1. Right away, I can see that the structure that we called A, structure A, has formal charges closer to 0. That alone tells us that structure A is the more likely structure. But what we can also see on structure B, carbon is given the most negative formal charge. The most negative formal charge should be on the element with the highest electronegativity, which in this case is nitrogen. So carbon would not have a more negative formal charge than nitrogen because nitrogen has the higher electronegativity. So again, we compare the electrons it has in the molecule with the ones that it has as the valence electrons it has on its own. We calculate the formal charge the same way as if these were ions, and we compare them. We want the formal charges to be the closest possible to 0, and any negative formal charges should be on the more electronegative atom. So since these charges were closer to 0 and the most negative charge was on the most electronegative atom, this is the more likely structure.